Welcome! In this explainer, we're going to pull back the curtain on one of medicine's most incredible inventions, X-ray imaging. We're going to uncover the amazing science that lets us literally peer inside the human body. It's a question we've all probably had at some point. How on earth can a doctor see your bones without making a single cut? Well, the answer is a wild journey into the world of high-energy physics, and we're about to take that journey together. The whole secret is creating a kind of sophisticated shadow, but with a type of light that our eyes can't even see. You see, dense materials like bone or, say, metal, they block a lot of this light, and that casts a bright white shadow on the final image. Softer things, like our tissue and the air in our lungs, they let most of that light pass right through, which is why they look dark. It's that simple difference, what gets blocked versus what gets through, that creates the entire picture. So to really understand how that shadow is formed, we're going to follow the entire life of a single X-ray photon. We'll trace its journey right from its violent birth, through its high-speed flight through the body, all the way to the final moment it makes its mark and helps create that image. Okay, let's dive into it. Our photon's journey begins right here, inside a vacuum-sealed glass device called an X-ray tube. This thing is the birthplace of every single X-ray used in medicine. Now, inside this tube, there are two key players. On one side, you've got the cathode, which basically acts like an electron gun. And on the other side, you've got the anode, which holds a metal target, and it's usually made of tungsten. The whole process is really just a high-speed collision between these two sides. And the process unfolds in a few crucial steps. First, a tiny filament is heated up until it literally boils off a cloud of electrons. Then a massive voltage is applied across the tube, and that launches those electrons at over half the speed of light. Finally, they slam into that tungsten target, converting their incredible kinetic energy into X-rays. And here's a wild fact for you. This incredibly violent collision is shockingly inefficient. I mean, more than 99% of the energy from those electrons is instantly converted into waste heat. So much heat, in fact, that the target actually has to spin really fast just to avoid melting. Less than 1% of all that power becomes the useful X-rays we actually need. So, that tiny fraction of useful energy is created in two very distinct ways. It all depends on exactly how the incoming electron interacts with the tungsten atoms in that target. And these are the two methods. On the left, you see an incoming electron that just misses an atom's nucleus. The powerful pull of that nucleus forces the electron to swerve and slam on the brakes, and it radiates its lost energy away as an X-ray. On the right, the interaction is a bit more direct. The incoming electron collides with one of the atom's own electrons, knocking it clean out of orbit, kind of like a game of atomic billiards. So that braking method is called Bremsstrahlung, which is just German for braking radiation. Simple enough, right? That swerving electron radiates its energy as an X-ray. The billiard ball method is called characteristic radiation. After an inner electron gets knocked out, an outer electron falls down to fill the gap, and when it does, it releases an X-ray with a very specific energy level, an energy that is a characteristic of the tungsten atom itself. And the result is this mixed beam of X-rays. The braking events create a broad curve of different energies, while the characteristic events add these sharp spikes at very specific energy levels. It's like an atomic fingerprint of the tungsten target. This whole cocktail of X-ray energies is what gets aimed at the patient. All right, so our photons have been created. Now they begin their most important journey, right through the human body, and this is where the image truly starts to form. As our X-ray photons travel, they get weakened or attenuated, and this is the key principle behind all of X-ray imaging. Attenuation just means that some photons are stopped by the body's tissues while others pass right through. And it's the difference between what starts the journey and what finishes it that creates the picture. Think of it this way. We start with an initial beam intensity, we'll call it I0. As it passes through the patient, some of that beam gets blocked. What comes out the other side is a weaker beam, which we'll call I. Dense stuff like bone is great at weakening the beam, while soft tissues, not so much. And this whole process is so predictable, it's governed by a precise mathematical rule called the Lambert-Beer law. This equation right here is the fundamental physics of the shadow. It lets us calculate exactly how much the beam will weaken as it passes through different tissues. But what's actually happening at the atomic level? I mean, why are some photons stopped while others just fly on through? Well, it really comes down to two main types of interactions. The first one, and honestly the most important for creating a clear image, is the photoelectric effect. Here, the incoming X-ray photon collides with an inner shell electron of an atom in the body. It transfers all of its energy to that electron, knocking it out of orbit. Now, the key here is that the photon is completely absorbed. Its journey is over. The second interaction is called Compton scattering. In this case, our photon just glances off a loosely bound outer shell electron. It loses a bit of energy and, crucially, gets deflected in a totally new direction. It doesn't get absorbed, it just gets scattered. So here's the bottom line. Photoelectric absorption, that's our friend. That's what happens when a photon is stopped by bone, creating that sharp white contrast we really want to see. Compton scattering, on the other hand, that's the enemy. Those scattered photons fly off in random directions and hit the detector where they shouldn't, creating a gray fog that just blurs the whole image. And what's really cool is that it turns out we can control which of these is more likely to happen. At the specific energy levels we use for medical imaging, the photoelectric effect, the useful one, is dominant, especially in dense materials with high atomic numbers, like the calcium in our bones. This is the physical reason we can see bones so clearly. It's not an accident. All right, so finally, the photons that actually survive this incredible journey through the body arrive at a detector. This is the moment where millions of individual photon paths are translated into one single, coherent picture. But getting a really sharp image means fighting a natural blurring effect called the penumbra. Think of it like the fuzzy edge of a shadow. To minimize this blur, radiologists use two main tricks: using the smallest possible X-ray source and positioning the patient as close as they can get to the detector. Both of those techniques make for a much crisper, clearer final image. And hey, remember those pesky scattered photons that create all that fog? Radiologists have a really clever trick for them too. They place a device called an anti-scatter grid right between the patient and the detector. It's basically like a set of Venetian blinds for X-rays. It physically blocks most of the photons that aren't traveling in a straight line, which dramatically cleans up the final image. So after that entire journey from the X-ray tube all the way to the detector, we're left with a detailed two-dimensional shadow. But that raises one final fascinating question. If an X-ray is just a flat shadow, how do technologies like CT scans use this very same physics to build a complete 3D model of the human body? Well, that's a story for another time. Thanks for joining us.